PU2 champions, so welcome to Dhurandhar Series, and in today's class we are going to do the one-shot revision for the chapter Chemical Kinetics. Now this chapter is super easy and highly scoring. If you just watch this one video, all your concepts will be cleared and you can get full marks in this chapter. So let's see what we have in today's class. So first of all, we will understand that what is chemical kinetics, okay? Next we will talk about the rate of chemical reaction. Next, we will discuss about the factors affecting the rate of a chemical reaction. Then we'll talk in detail about the effect of concentration, effect of temperature, effect of catalyst, and at the end we'll study about collision theory. Okay, so let's start with first understanding that what is chemical kinetics. So here we will cover two topics, that is what is chemical kinetics and the classification of reactions. Okay, so let us first understand that chemical kinetics is a branch of chemistry that studies the rate of a chemical reaction. Now rate means what? You can consider it as the speed of a chemical reaction. One particular reaction is either slow or fast, how much slow, and how we can change the factors or how we can influence the rate of the reaction or speed of the reaction, and also we talk about the mechanisms of the reaction. Okay, so it basically deals with three things: the speed of the reaction, factors affecting the speed of the reaction, and the reaction mechanism. Okay, now we will discuss about the classification of reactions. Okay, so we can classify on the basis of two parameters. One is on the basis of speed and on the basis of number of steps. Okay, now on the basis of speeds we have very fast reactions, very slow reactions, and moderate reactions, and on the basis of number of steps we have elementary reaction and complex reactions. Okay, so now let us first see this one, that is the type of reactions on the basis of speed. Okay, very fast reactions means those reactions which can be covered within 10 to the power of minus 14 to 10 to the power of minus 17 seconds. Okay, now let me tell you, you need to just remember one examples. This time period is not that important, but yes, you have to remember these examples. Okay, so if you add NaCl to AgNO3, immediately you will observe the precipitation of AgCl. Now coming to moderate reactions which can take minutes to hours, like inversion of if you break sucrose, like if you break this one, that is sucrose with water, you will get glucose and fructose, right? This is a moderate reaction. And there are certain reactions which is very slow and take months to years. An example here is rusting of iron or formation of coal. Okay, now let us talk about the types of reaction based on the number of steps. So here we have two reactions, one is elementary reaction and the other one is complex reaction. See, this is important. Elementary reaction is those reaction which can occur in one single step. Okay, one single step, the reaction is over. In that, what happens? Reactions taking place in one single step are called as elementary reactions, and only one step, so it is itself is elementary. So these all points definitely like means the same thing, that the whole reaction takes place in one step. Now what is complex reaction on the other hand? When a sequence of elementary reactions gives the final product, it is called a complex reaction. When you have more than one steps. Okay, for example, if I have a reaction A gives B, then B gives C, and the final reaction I get is A gives you C, right? So in these reactions you have two steps involved. So such type of reactions, and each of this step is an elementary reaction, right? So those reactions where each step behaves as an elementary reaction, and we have a number of reactions in the whole I can say in the reaction mechanism, those type of reactions are called as complex reactions, right? And each individual step is an elementary reaction. Now here, out of these all steps, there will be one step which is slowest. Okay, which is the slowest step. Now that slowest step will determine the rate of the reaction. Means if you have 5-6 steps, then the speed of the reaction will not depend on all the steps, rather it will depend on the slowest step of the reaction. Okay, now once we have understood what is chemical kinetics and what are the types of reaction, now let us move towards to understand what is rate of a chemical reaction. See, rate, basically simple word you have to understand, is the speed of a reaction. Okay, what is the formula of speed in physics? It is distance covered by time taken, right? In a reaction, what happens? Reactants gets converted to product, right? And reactant concentration decreases with time and product concentration increases with time. So the rate of a reaction or the speed of a reaction is defined as the change in concentration by time taken. Now this change in concentration can be for reactants also, can be products also. Now, if you have a particular reaction, A plus A gives you B, then the disappearance of A, because this is reactant, right? It will slowly, the A concentration will decrease. So it will disappear. So rate of disappearance of A is equal to change in concentration of A by change in time. Now why I have given a minus sign here? This is very, very important. See, in reactant, what will happen? The concentration of A will decrease. Like for example, initially it was 5 moles. For example, after the reaction it is 3 moles, or after some time in 10 minutes it has become 3 moles. Now what is the change in concentration of A? Final minus initial. So 3 minus 5 will give me minus 2. So that will give me rate in the negative term, which is not possible. Rate is a positive quantity. So to balance out this negative thing, we have to add a minus sign. And remember, this is only for reactants. Okay. Next, you have rate of appearance of B, means the production of B. So how will B be produced? For that you need to change in concentration of B by change in concentration of time. Now here, since the B concentration will increase, this quantity is a positive quantity. Now let's talk about concentration versus time, how we can show in the graph the rate of a reaction. So as you see, with time the reactant concentration will decrease and the product concentration will increase, and this is the graph for concentration versus time for a reaction. Okay, now we will discuss about types of rate of a reaction. See, we can discuss the rate of a reaction can be average. You can also calculate average rate, and we can calculate instantaneous rate. Now what is this? We will see in the next slide. Then we'll talk about differential rate equation and the unit of rate of reaction. So first let's talk about this average and instantaneous rate. Now see, average rate means what? When you calculate the rate of a reaction in a certain time interval, there's a measurable time interval. For example, in 10 minutes, 20 minutes, 5 minutes, you have started a reaction at 10:30, and then after 10:40 you want to check the concentration. When there is a certain interval of time, the time interval is a measurable quantity. At a certain interval of time, when you measure the rate of the reaction, that is called as average rate. Okay, and how we denote it? We denote with this triangle. Now comes to instantaneous rate. Now instantaneous rate is that rate which is measured at a particular instant. Okay, you are not waiting for a time interval. You want the rate of the reaction at 10:40 am dot. Okay, that is called as instantaneous rate. When you measure 10:30 to 10:14, that 10 minutes interval, that becomes average rate. But when I want to know the rate at 10:40 dot, that means it is your instantaneous reactions or instantaneous rate. Okay, and how do we denote that? It is denoted by d by dt. Okay, means for example, there is a, okay, we'll explain this in detail in the graph. Now you can see this graph. Okay, so first of all, understand that this graph concentration is decreasing. So this graph is for reactants, right? And here the concentration is increasing. So this graph is for products. Okay, now in the same graph, I'll show you how we can calculate instantaneous rate and average rate. See here, when you take a particular time interval, for example, T1 and T2. At T1, the concentration is R1, and at T2, you can see the concentration is R2, right? This is T2 graph. I am highlighting here, and this is the graph for T1, right? So what will happen? What is the rate, average rate? It is minus. I told you for average, we have to use this symbol of triangle. Triangle, concentration of R divided by concentration of T. So what will happen here? Minus the constant. What is the initial concentration? R1. The final concentration is R2. So you have minus R2 minus R1 divided by T2 minus T1. So now here that will be, it can be written as, so this is the formula for average rate. Now if I want to calculate the rate at one particular instant T, okay, at any particular instant T you want to calculate the rate, then it is minus dr by dt. So for example, at this point the concentration is R, then minus dr by dt, which is equal to slope of the tangent. So how will you calculate the instantaneous rate? By taking the slope at this tangent. Okay, this is, you have to draw a tangent at that particular time point, and then you have to calculate its slope. Okay, now same thing for products also we can do. In products the concentration will increase. So if I want to calculate the average rate, I can take one particular interval T1 and T2, and there suppose I have P1 and I have P2. So what is the value of rate here? Average rate. So final concentration is P2, initial concentration is P1. So P2 minus P1 by T2 minus T1. Okay, that is there. And then when you have to calculate the instantaneous rate, okay, instantaneous rate at that particular interval. So you have to draw a tangent here. Okay, and then you have to calculate dp by dt is equal to slope. Okay, you have to draw the tangent of that particular curve at that particular point, and then you can calculate the instantaneous rate, and that will be also given you by the slope of the tangent. Clear? So average rate, how to calculate? By taking two time intervals, their corresponding concentrations and then taking the difference and dividing them. Instantaneous rate, how to calculate? You have to draw a particular at a particular point where you want to calculate the rate. There you need to draw a tangent and then you have to calculate the slope of the tangent. Okay. Now we have understood what is average rate and instantaneous rate. Now let's talk about differential rate equation. So let us consider that you have a general reaction like this: A plus B gives you C plus dt. Now the rate of this reaction can be written as, see, rate is equal to minus whatever coefficient is there, that will go in the denominator. Okay, since these are reactants, here these are reactants, right? So here we have to use the sign minus. So minus 1 by A dA by dt is equal to minus 1 by B dB by dt is equal to, now for C I have to use the sign plus because it is on the product side. So plus 1 by C dC by dt is equal to plus 1 by D dd by dt. Okay, now let me give you an example here so that we can understand it in a better way. So, okay, yeah, I have a worked out example here. Let us solve this question. See, for N2 and 3H2 gives you 2NH3. If the rate of appearance of NH3 is given to me, then what is the rate of disappearance of H2? Okay, so first let us write the reaction here. Okay, so we have N2 plus 3H2 gives 2NH3, right? N2 plus 3H2 gives you 2NH3. Now what is the rate of this reaction? Rate I can write, since there is no coefficient here, so minus d N2 by dt, okay, is equal to, for H2 there is a coefficient of 3, so minus 1 by 3 dH2 by dt is equal to plus 1 by 2 dNH3 by dt, right? Now what we can do, you can see that the value, they have asked you what? Disappearance of H2, and they have given you the value of NH3. So we need a relation between H2 and NH3. So just pick out those from the equation. So I can write that minus 1 by 3 dH2 by dt is equal to plus 1 by 2 dNH3 by dt. Okay. Now minus dH2 by dt is equal to 3 by 2 dNH3 by dt. Okay, so that will equal to 3 by 2 dNH3 by dt is 4 into 10 to the power of minus 3. Okay, so that will give me equal to 6 into 10 to the power of minus 3. So what is the rate of disappearance of H2? It is 6 into 10 to the power of minus 3 mole liter inverse second inverse. Okay, so I have got the answer. So by applying this formula, you can easily solve the question. Now let's talk about units of rate of a reaction. Okay, so if you see, what is rate? Rate is nothing but concentration, right? Concentration by time, right? Concentration is taken in molarity. So the concentration, I can write the concentration unit is mole liter inverse, and then I have time. Time will be written as second inverse. Now this mole liter inverse can also be written as molarity, so MS inverse. Now what we have, now if the reactants are in the gaseous state, okay, if the reactants are in the gaseous state, then how do we represent this concentration? In the terms of ATM, not in the molarity, in the terms of pressure. So if the reactants, okay, if the reactants are in gaseous state, okay, then the rate will be represented as ATM second inverse. Clear? Okay. Now let's talk about the factors affecting the rate of a reaction. So basically 3 major factors are there, but in total we have 6 factors. So let us understand one by one. So first is concentration. If the concentration will increase, the rate of the reaction will increase. Okay. The rate depends on the concentration of the reactants. If that increases, rate will increase. The next factor is temperature. Again here, if the temperature increases, the rate of the reaction will increase. Okay. Increasing the temperature always increases the rate of the reaction. Next is nature of the reactants. Okay, the intrinsic reactivity depends on the bond strength and molecular structure. See, reaction is basically what? Reaction is breaking of bonds and forming of bonds, right? You have to break the bonds and you have to form new bonds. So if the bonds of the reactant are very strong, then the reaction rate will be slow because you need more time to break those bonds. On the other hand, if the reactant's bonds are weak, then it can be easily broken and the rate of the reaction can increase. So that is why the nature of the reactant also affects the rate of the reaction. Then we have the next factor, that is catalyst. Okay, so what is catalyst here? Catalyst also increases the rate of the reaction. Then surface area. So for reactants in different phases, a greater surface area increases the rate of the reaction. When the surface area is more, reaction will be faster. And then radiation. Some reactions are initiated or accelerated by photons or UV light. So for example, if you know free radical reactions, okay, if you do simple halogenation of chlorine to an alkane, okay, so in that you need UV light or you need this photons energy. So those type of reactions depend on the energy of the radiations. So what are the 6 factors that we have studied? First is concentration, then we have temperature, then we have catalyst, nature of the reactants, surface area, and lastly radiations. But in this chapter we will study 3 factors in much detail. Okay, we'll go to the depth of these 3 factors. So the first one there is concentration, then we'll study about temperature, and then we'll study about catalyst. Okay, so these 3 factors are the major factors and is applicable to all the reactions, so we'll study them in detail. So now let us move forward with the first factor in detail, that is effect of concentration. Okay, so in this, what all things we'll cover? First we'll understand what is rate law and rate constant, then we'll talk about order and molecularity, we'll talk about integrated rate equation, then we'll talk about half-life and pseudo first order reaction. Okay, so let us start with the rate law and rate constant. So see, rate law, how will you understand what is rate law? It is a very simple thing. Rate law is an expression. First of all, what is it? It is an expression which gives you the relation between the rate of the reaction and the concentration of the reactant. Okay, we understood that there is a major factor which affects the rate of the reaction is the concentration. So how the rate is dependent on concentration, that equation, that relation is given by this rate law. Clear? So for example, if I have a reaction like this, A plus B gives you product. So rate law, remember, is always relating the concentration of the reactants, not the products. Okay, reactants and rate, that relation is given by rate law. So here I can say that, see, rate of the reaction is proportional to the concentration of A and concentration of B. Okay, here we give X and Y something. Okay, what is that? We will understand in a few slides. So rate is proportional to A because A is a reactant here, B is a reactant here. So proportional to A to the power of X and B to the power of Y. Now to remove this proportionality, we multiply a constant which is called as rate constant. Okay, so now we'll understand all the parts of this equation. K is your rate constant, and remember it is temperature dependent. Okay, K is temperature dependent. Then A is the molar concentration of the reactants. What is this X and Y? This X and Y represents the order of the reaction. Okay, now determined experimentally and are not necessarily equal to A and B. So X and Y, okay, X and Y are nothing but order. What is order? We will discuss, but remember that it is determined experimentally and it is may or may not be equal to A and B. Means A and B is what? Their coefficients, right? Stoichiometric coefficients. It may be equal to A but may not be equal to A also. Clear? So what is rate law? Rate law is an equation, is an expression which relates the rate of the reaction to the concentration of the reactants. Okay, fine. Now let's define what is rate constant. Okay, what is rate constant? See, rate constant is equal to, so what will be equal to rate constant if these concentrations are 1 molar? Okay, then the rate, when all the concentrations are taken as 1 molar, whatever rate we get, that is called as rate constant. So the value of rate constant K is equal to the rate of the reaction when the concentration of each reactant is unity or 1 molar. Okay, now let's move forward to the characteristics of rate constant. This K value, very, very important. Some characteristics you should know. It can be asked in the MCQ. It indicates the speed of the reaction. Means if K value is high, then rate of the reaction is high. Okay, next, greater the value of rate constant, faster is the reaction. Next, every reaction has a particular value of rate constant at a particular temperature. Okay, because this rate constant is dependent on temperature. So if you do a reaction at one temperature, it will have a specific K value. If you change the temperature, it will have a different K value. Next, the rate constant for the same reaction differs with the temperature. Yes, if you are doing the same reaction in 2 different temperatures, the K values will be different. Basically, because the K depends on the temperature. Next, the value of the rate constant for a reaction does not depend on the concentration of the reactants. Rate constant does not depend on the concentration of the reactants, it only depends on the temperature. Now the unit of rate constants depends on the order of the reaction. So here let's talk about the unit of rate constant. See, if you see, I write a reaction like this: rate is equal to k into a to the power of n, for example. Then what will be k equal to? K is the rate by a to the power of n. Now what is the unit of rate? Mole, liter inverse, second inverse. And what is the unit of a? A is what? Mole, liter inverse to the power of n. Now what will happen? Here we will have a common point, so I can write mole here 1 minus n. Okay, liter, here I have n minus 1, second inverse. Mole 1 minus n, liter n minus 1, and second inverse. Now let's talk about order and molecularity. So we have been listening this word order for a few times. So what is order exactly? So whatever this x and y we write in the rate law, these are called as orders. Okay, so x is the order with respect to a, y is the order with respect to b, and the overall order of the whole reaction is x plus y. Okay, now it is an experimental concept, means x and y is determined experimentally, and it can be a whole number, zero, or even a fraction. Okay, and it applies to both elementary and complex reactions. Now let us understand what is the significance of rate. Okay, this is very, very important to understand that what exactly this order tells us. What is its significance? See, I told you that if you increase the concentration, the rate will increase. But by how much? Means if you double the concentration, will the reaction rate will also be doubled, or it will become 4 times, or it will have no effect? That is what is given by order of the reaction. So see, the order tells us precisely how the reaction rate changes when the concentration of the reactant changes. You are definitely changing the concentration of the reactant, but how does it affect the change in the rate of the reaction? By how many times the rate will change? That is given by order. So for example, if it is a first order reaction, if you double the concentration, the rate will also double. But if it is a second order reaction, if you double the concentration, the rate will become 4 times, right? So that is the order of the reaction. Now here is one example: rate is equal to k a to the power of 1 by 2 b square. And what is the overall order here? So you can see overall order is 1 by 2 plus 2, that is 2.5. So overall order is 2.5 for this reaction. Now let's talk about the rate law, like for different conditions. So if it is a zeroth order reaction, so what is rate? Suppose imagine that this is a reactant, A gives you products. Okay, then what is rate? Rate will be equal to k into a to the power of n, right? Now if n is a zeroth order reaction, then what I will get? Rate is simply equal to k. And there are some examples of zeroth order reaction. So if you have H2 plus Cl2 in presence of H nu, that gives you 2HCl. Then if you have 2N2, it decomposes to give you N2 plus O2. So these are all examples of zero order reaction. Now similarly for first order reaction, rate is equal to k into a. Here decomposition of H2O is an example of first order reaction. Now you may ask that, ma'am, how to identify this one? As we have discussed, you cannot predict by seeing a reaction whether it is zeroth order or first order or second order. You have to do it experimentally. So for exam, you have to remember the examples. Okay, you cannot see a reaction and tell whether it is a first order or a second order. But yeah, there are certain category of reactions. For example, surface catalyzed reactions. These are always zeroth order reactions. Like that you can know. Okay, but it is not that only the surface catalyzed reactions are zeroth order. There are other reactions also. Now coming to second order reaction, the formation of carbon monoxide, decomposition of NO, these are all your second order reactions. Okay, so basically here more focus should be on these expressions, how we can write the rate law for zeroth, first and second order reactions. Now let's talk about molecularity. See, order was a experimental concept. You have to do the experiment and you have to calculate the order. But here molecularity is a theoretical concept that applies only to single elementary reaction steps. Order, as we discussed, can be for both complex and elementary reactions, but molecularity concept is added or is used in one single step of a reaction. It basically describes the number of reactant species that collide simultaneously to form the product in that step. Okay, so how many reactants are reacting, that is the molecularity of the reaction. For example, here only one reactant is reacting, here molecularity will be 1. Here you have 2 moles of HI, 2 molecules, so that is molecularity is 2. Here 2 NO and 1 O2, so the molecularity is 3 here. Okay, now let us see the difference between order and molecularity. So order, what is the definition? It is the sum of the powers of concentration terms in the rate law. So X and Y, if you add them, that is the overall order of the reaction. Then what is molecularity? It is the number of species reacting in an elementary step. Now order can be 0, fraction or even an integer, but always molecularity is a whole number. Then method of determination, this is determined experimentally and this is determined theoretically from the reaction mechanism. What is the application? That application is both for elementary and complex reactions, and this is only for elementary reactions. And one more important thing, that it can be 0 and this cannot be 0. Okay, now we will talk about integrated rate equation. Okay, so before that, have we discussed the unit of rate constant? Yes, I think we have already covered that. Okay, so let's move forward to the integrated rate equation. Now see, by this time what we have studied is what will be the rate. Like you have started at a particular time and you ended at a particular time, and you can just calculate the rate of the reaction. But what if you want to predict that, suppose I have started a reaction at 10:30 and after 60 minutes what will be the concentration, or suppose you have already known the concentration. For example, you have started a reaction with 5 moles and you want to know that at what time or after what time it will become 2 moles. So when you want to calculate the concentration of the reactants or the concentration of products or time, okay, so for that we need integrated rate equation. See here, the rate laws we have seen describe the instantaneous rate of the reaction, d by dt we are doing, which is the instantaneous rate. To find the concentration of the reactants after a certain amount of time has passed, we need a different form of the equation. So if you want to calculate that after 10 minutes what will be the concentration, after 30 minutes what will be the concentration, you want to calculate, for that we need a different set of equation which are called as integrated rate equations. Okay, so it is derived by using the calculus to integrate the differential rate laws. They express the reactant concentration as a direct function of time. So this integrated rate laws, here the concentration and time, there is a direct relation between them, and each reaction order 0, first and second has its own unique integrated rate law. For 0th order we have a special integrated law, for the first order we have a special integrated law. Okay, so differential rate law, when you do calculus and you integrate it, you get the integrated rate law. So that is how the name has come. Now let's talk about the applications of this integrated rate law. As I told you, to calculate how long it takes for a reaction to progress. So suppose you know the initial time and you know the final concentration. For example, you started with 50 mole and you want to stop at 4 moles. So for that, how much time will be required if you want to calculate that? Or if you want to determine the amount of the product or reactant present after a certain time interval. After 30 minutes, how much reactant will be present, how much time will be present, how much product will be produced, that you want to calculate. Or simply to determine the order and rate constant of a reaction. To find out the rate constant of a reaction also, we can use the integrated rate equation. So we will be studying in our syllabus 2 important orders, 0th order and first order, in detail. We will see their integrated rate laws and how from calculus we can derive that also we will see. So let us start with the first 0th order reaction. What do you mean by 0th order reaction? So this is important. So let me just highlight this one. Okay, so 0th order reaction means that the rate of the reaction, okay, is proportional to 0 power of the concentration or reactants. Means basically here what we mean, that the rate, okay, the rate is independent of concentration, independent of concentration of reactants. That is the significance of the 0th order reaction. So now how we can derive it? Suppose let us assume that a reaction is given, R gives you P. Then rate will be equal to minus dr by dt, and that is equal to k into r0, right? So now you can, like for example, after this I can write for this one, rate is equal to minus dr by dt and rate is also equal to k into r into 0. So I can equate both of them, right? See, here I can write first equation. From the given equation I can write rate is equal to minus dr by dt. Okay, then rate is also equal to, since it is a 0th order reaction, k into r0, or that is equal to k into r, right? So I can, sorry, not k into r, only k, right? So you can now equate these two equations, minus dr by dt and k. These two equations you can equate, right? So what I will get, minus dr by dt is equal to k. Now what I will have, now you can just integrate this. So rate is equal to minus dr by dt, just multiply this dt on this side. Okay, so what I'll get, dr is equal to minus k dt, also negative sign I have brought to this side. Now if you integrate both sides, if you integrate dr, you will get r, and here I will integrate kt plus I. Now remember, I is a integration constant. Okay, and to find the value of I, what you have to do, you have to consider time equal to 0. Means when you have just started the reaction, at that time what will be the value of r naught, where r naught is the initial concentration of the reactant. See, you have to now find the value of I. So for that, what you have to do, you have to assume that let's the time be equal to 0, and when time equal to 0, r is equal to r0, which represents the initial concentration. When you started the reaction, what is the value of the reactant? So for that, if you substitute here, r will be replaced with r naught minus k, t is equal to 0 plus I. Then this one will become 0 and I will be equal to r naught. Now substituting the value of I in the equation, you have r is equal to minus kt plus r naught, right? So this is the equation for your 0th order reactions. You can just formulate it better like this, r naught minus r is equal to k into t. This is the integrated rate law for 0th order reactions. Here r naught is the initial concentration, r is the final concentration, k is the rate constant, and t is the time, right? So now if I want to draw a graph for this one, so let us see, suppose you want to draw a graph for r, okay, versus time. I'll teach you how to draw the graph, so that for any question you can draw, you don't have to remember this one. So see, the graph of a straight line is equal to what? Y is equal to mx plus c. Now whichever x versus y it's given, okay, whatever is given to you, the first one r, okay, that comes under y axis, okay, and the second one comes under x axis. Okay, first two things clear, this equation is clear, this one is clear. Next, what you have to remember, what is the equation we have? We have r naught minus r is equal to k into t, right? Now what you have to do, you have to keep the y on the left hand side and everything else on the right hand side. So what is your y? Y is r. So I can write this equation, r is equal to r naught minus k into t, right? Or I'll just write it little bit more in the equation form. I can write it like minus kt plus r naught, right? Now this equation is what? Y is equal to minus mx plus c. You can relate this with the straight line equation, right? Or so what is, or just y is equal to mx plus c. So r will be on the y axis and t, which is your x, that will be on the x axis. Now after that you have slope of minus k. This slope value is minus k, and then you have c, that is your r naught. Where is it? This value. This value is cutting your y axis, and that is your r naught, right? We got this one. Now let us see one example. So I have told you that the surface catalyzed reactions, okay, surface catalyzed reactions are generally 0th order reaction. Now what is the reason behind that? So we have an example. If you take NH3 and treat it with at such a high temperature and catalyst, you will get N2 plus 3H2, right? This reaction, what happens? The NH3 is absorbed on the platinum surface and then it breaks you to give you N2 and H2. Now see, in this reaction, platinum metal acts as a catalyst, and at high pressure and temperature, the metal surface gets saturated with the gas molecules. Okay, so which gas molecules? Now this metal is there, on that the NH3 molecules are already getting absorbed. Okay, so a further change in reaction conditions is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of the reaction independent of its concentration. Now for example, in this platinum surface, okay, there are 5 spaces, okay, there are 6 spaces, okay. Now already the 6 spaces are filled. Now even though you increase the concentration of ammonia, there is no place to get absorbed on the platinum surface. So even though you increase the concentration of ammonia, the rate will be only due to these 6 ammonia which is already absorbed, right? So in this case, the concentration is not affecting the rate of the reaction. So that is why such reactions are your 0th order reaction. Similarly, decomposition of Hi on gold surface to give you H2 and I2 is also an example of 0th order reactions. Okay, now let's move to first order reaction. Okay, we'll derive it accordingly. So you can see first here, See, those reactions whose rate depends upon the concentration term of the reactant, okay, directly equation. So you can see if R gives you P, then I can write rate is proportional to R, okay. So I can write minus dr by dt is equal to kr. How I'm getting this equation? So I'll again show you here first, then I'll erase it. See, R gives you P means first I can write rate is equal to minus dr by dt. This is the differential rate law we have already studied. Then I can also write, since it is a first order reaction, it is equal to K into R. Now this is my equation 1, this is my equation 2. So I can say that minus dr by dt is equal to Kr. Getting this one, how we have got? Okay. Now let's move to the next one, that is integrating both sides of the equation. Okay, if you integrate on both sides, what you will get? Minus dr by d. So what I'll do, first I'll take R on this side and I'll multiply T on this side. Okay, I'll do a cross multiplication here. So minus dr by R and k dt. Now when you integrate both sides, minus dr by R and k dt, you will get this integration will give you minus ln R plus kt into I. Okay, here there is only one minus, not two. Yeah, so minus ln R plus kt I. Now this I is what? It is your integration constant and you have to find the value of I here. So to find the value of I, what we'll do? We'll assume t equal to 0 and R is equal to R0 at that time. So if I substitute t equal to 0, then I will get I is equal to minus ln R0. Here it will be R0, like R will be substituted with R0, t is 0, so I equal to minus ln R0. Now if I substitute this value in the equation, in the first equation, where is my equation 1? This is my equation 1, right? So I'll get minus ln R is equal to kt plus I, right? So I will substitute at ln R naught. So minus ln R is equal to kt minus ln R naught. Now what I'll do, I'll take this one to left hand side. So you'll get ln R naught minus ln R is equal to kt. So ln R naught by R is equal to k into t. Okay. Now here how I can calculate t value? It is 2.303 by k log R naught by R. Okay, so if you consider, if you generally see, log terms are more common in the reactions, right? So we can convert this ln to log by just simply multiplying it with 2.303. So 2.303 by k log R naught by R is equal to t, and this is the main equation. Okay, now unit of k will be what? See, here a slight error is there. If you calculate, unit of k will be second inverse. Okay, I'll show you how. Then this R naught by R can also be represented in the form of A by A minus X. Means A is what? The initial concentration. Suppose X amount has reacted. So what is the final concentration? A minus X. Okay. So now let us see the graph that we have to draw. Okay. So first of all, if the graph is for, you have this equation, the graph is for ln R versus T. Okay, now I have told you already how to find out the graph. So let us first write our equation. What is our equation? Kt is equal to ln of R naught by R. This is the value of Kt, right? This can be written as Kt is equal to ln of R naught minus R. Sorry, minus ln R. Okay, Kt is equal to ln of R naught minus R. Now you need this equation, ln R on one side and T on one side. So I'll take this ln R on this side. Ln R is equal to minus Kt plus ln of R naught. Now I can get Y is equal to mx plus C. Okay, now here you can see that you have Y, ln R is on the Y axis and this one T is on the X axis, right? So what is this value here? The slope of this equation is minus m, like minus k, right? So the slope value is minus k here. Okay, and this one, this value is C, the y-intercept, that is your ln R naught. Okay, so you have Y is equal to mx plus C. Now that is how we can draw this equation. Now let's see another equation. If you have to draw for log R naught by R, log R naught by R versus time. So how we can solve this one? So the equation is Kt equal to 2.303 log of R naught by R. Okay, so that gives you log R naught by R is equal, I can write this equation, reframe it, log R naught by R is equal to K by 2.303 into T. So this you can see Y is equal to mx. I'm writing the equation, right? So what is my Y here? Log R naught by R. and T is your slope here. Okay, now what is the slope here? K by 2.303. So that gives you a straight line. You can see there is no C here, so no intercept. The graph will pass through the origin. Clear? So that is how you don't have to remember the graph. You can easily draw it if you know the trick how to draw the graph. Now let's talk about some examples of first order reaction. So first one is hydration of ethene. If you add hydrogenation of ethene, so that is a first order reaction. All natural and radioactive decays, okay, all the natural and radioactive decays are first order reaction. One example here, radium gives you helium and Rn, so here also it is a first order reaction. That is the second example. And decomposition of N2O5 and N2O are also the examples of first order reaction. Now you need to remember these examples. It can be asked in MCQs, or simpler question can be asked, like write 2 examples of first order reaction. Then you need to know at least 2 examples for all the order of the reactions. Now let's have a I can say cumulative or all the theories, concepts that we have studied till now. So for zeroth order reaction, the order is 0. And what is the unit of rate constant? So for unit of rate constant, you have this formula, moles 1 minus n, liter n minus 1, second inverse, right? If it is a zeroth order, substitute n is equal to 0. So we'll get mole, liter inverse, second inverse. That is the unit here. Next, for first order, just substitute here 1 everywhere in place of n. So you'll get second inverse. Then for second order reaction, substitute 2 here. So 1 minus 2 is minus 1. So mole minus 1, liter is 2 minus 1 plus 1 and second inverse. Okay. Now let's talk about half-life. What is half-life? From the name itself, you can understand half-life is the time required for the reaction, for the reactant to come to its half of the initial concentration. Means suppose you have started with 100 grams. So how much time it takes to come to 50 grams? The time required for the reactant to reduce to its half is called as your half-life. So of a reaction is the time required for the concentration of the reactant to be reduced to 1/2 of its initial value. Okay, it's convenient way to describe the speed of the reaction. A shorter half-life means a faster reaction. That's the application of half-life. Now let us see the formulas of half-life. So for zeroth order reaction, the formula is A0 by 2. How I'll derive you and show. So for remember that for a zeroth order reaction or any order reaction, you can calculate the half-life. You have to remember that this R or this value, that will be equal to R0 by 2. Okay, that you need to know here. So now if I calculate for zeroth order, what was the integrated equation for zeroth order? A0 minus A is equal to KT, right? So here A0 is there, minus what is the value of A now? It is A0 by 2, okay, is equal to K into T is what? T half. So now 2 minus A, that is A0 by 2K. So you will get T half is equal to A0 by 2K. Now coming to the next one, for first order reaction, what is the formula? KT is equal to 2.303 log of A0 by A. Again here what it will be? A is A0 by 2. So 2 will go up, right? So I can write K into T half is equal to 2.303 into log of 2 I'll get. Now log 2 is 0.301 and if you multiply you will get 0.693. Okay, so T half is equal to 0.693 by K. Okay, and one more thing you need to know, that in general T half is proportional to 1 by A0 to the power of n minus 1. Okay, so this is not applicable for first order, for except for first order. For all other orders you can calculate that T half is proportional to 1 by A to the power of n minus 1. Okay, so you have to remember this formula. So let me just remove all this so that we can focus on the formulas only. So what is the formula for zeroth order half-life? So you can see that for zeroth order the half-life is T0 is equal to A0 by 2K, and for first order it is 0.693 by K. Okay, now let's move to something called a pseudo first order reaction. See, what is a pseudo first order reaction? A pseudo first order reaction is a reaction that appears to be first order but is actually a second order. Okay, it appears to be first order. Why it appears to be first order? Because one of the reactant is actually present in excess. Okay, so it happens when one or more reactant is present in much larger concentration than the other reactant. See, suppose A plus B is giving you C, okay, and B is present in excess. Okay, when it is present in excess, See, when too much B is present, if you change the concentration of B, if you add slightly B or if you remove slightly B, it doesn't overall affect the rate of the reaction because it is too much in quantity, right? So the B is not affecting the concentration of the, is not affecting the rate of the reaction because it is present in too much amount. But the concentration of A is actually affecting the rate of the reaction. So that is why even though both are responsible, but the majority change. If you change A, the rate of the reaction may affect, but not with B. So that is why it appears to be a first order reaction, because the rate is determined only with the concentration of A and not the other one B, and but it is actually a second order reaction. So here we have two examples. One is your hydrolysis of ethyl acetate and the second one is the inversion of cane sugar. So if you see acid catalyzed inversion of cane sugar. So if you have taken only cane sugar and you have added excess of water in acidic medium, so that will break and give you glucose and fructose, and the rate is equal to K into only the concentration of sucrose, first order, not the water. Similarly, in the acid catalyzed hydrolysis of ethyl acetate, if you take only ethyl acetate and water in excess with H plus, that will give you acetic acid and alcohol. And this one again depends only on the ester concentration and not on the water concentration. So this is also a pseudo first order reaction. And now we will go to the next important factor, that is effect of temperature, right? So now see here that temperature for a chemical reaction, with the rise in every 10 degree, the rate constant is nearly doubled. So what is the effect of temperature? If you increase the temperature by 10 degree, the rate constant almost gets doubled. Okay, so in temperature we'll study about Arrhenius equation and Boltzmann curve. Okay, so let us start and understand what is Arrhenius equation. So now if you remember, there is one factor was concentration, and to relate the rate of the reaction and concentration, the expression that was used was rate law expression. Now similarly, to draw a relation between the rate of the reaction and the time and the temperature, sorry, to give a relation between the rate of the reaction and the temperature, we have an equation called as Arrhenius equation. Okay, the temperature dependence of the rate, how the rate depends on the temperature, is accurately explained by Arrhenius equation. So what is the Arrhenius equation? K equal to A into e to the power of minus EA by RT. Now what are these terms here? First of all, understand this K. Okay, I'll write here all the terms. K, as we know, this is the rate constant. Okay, next I have A. A is called as pre-exponential factor. Pre-exponential factor. Next we have EA, which is called as your activation energy. Okay, and then R is gas constant, universal gas constant, which is equal to 8.314. Then you have T, which is your temperature. Okay, now before understanding these all terms, let us understand that what was the Arrhenius theory of a reaction. See, Arrhenius said that any reactant will not convert to product directly. Okay, any reactant will not convert to product directly. When a reaction happens, the reactants reach an intermediate state. Okay, and then from that intermediate state, they get converted to the product state. Okay, so you can see here, first or intermediate state, or you can say when activated complex is formed, when the reactants will react, first they form an activated complex and then they get converted to products, not directly. So activated complex is a complex which is having higher energy than the reactants. So the energy that is required for converting the reactants to activated complex is called as your activation energy. Now you see H2 and I2 is there. So first they will convert to this activated complex C. So what is this activated complex? Also let me show you. It is something like this. Okay, where the bond between H and I is forming and the bond between H2 and I2 is breaking. Okay, so this activated complex is formed first. Now for this activated complex, whatever energy is required, that is called as activation energy, and after that, that gets decomposed and you find the final product 2HI. Okay, so what we have understood, you can see that this EA, okay, this is what the activation energy is here. Now let's talk about the graph of this equation. So if you take ln on both sides, you'll get ln k is equal to ln A minus EA by RT. And here you can see this is Y and this is X, right? How I can write? I have ln K is equal to minus EA by R into 1 by T plus ln of A. Okay, so you have Y is equal to mx plus C. Now m is equal to what? Minus Ea by r, x is equal to 1 by t, and here I have ln k. Okay, ln k is equal to mx plus c. Now we'll talk about when you have two different temperatures. We have studied in the first also, when you for a same reaction at two different temperatures, you will have two different k values. That is because temperature is highly affecting the rate of the reaction, and higher temperature, higher k value. So for two different temperatures we have this formula, and this is what mostly we will be using for numericals also. Okay, so log of k2 by k1. What is k2? The rate constant at t2. Log k2 by k1 is equal to Ea by 2.303 r into 1 by t1 minus 1 by t2. Okay, log k2 by k1 is equal to Ea by 2.303 r 1 by t1 minus 1 by t2. Okay, now coming to Boltzmann curve. So see, what is this Boltzmann curve and why we are studying this? So this we are studying to understand that when we increase the temperature, why the rate of the reaction increases. Okay, temperature we have understood that when we increase temperature, the rate of the reaction definitely increases. But what is the logic behind it? That is explained by Boltzmann curve. See, Boltzmann curve says that when you have a fraction of molecules which are undergoing reactions, okay, these fractions of molecules, all the molecules do not have same energy. Okay, some molecules have very low energy, some molecules have very high energy, and there is a like I can say one average energy that majority of the particles possess this value of energy. Okay, so that is your, this is called as most probable kinetic energy. Means if you have taken 100 particles, majority of the particles will have energy of this value. Okay, and this is called as your most probable kinetic energy. On the other hand, some particles have lower energy and some particles will have higher energy. Very less particles will have lower energy, very less particles will have higher energy, and majority of the particles will have one energy, which is called as the most probable kinetic energy. Now what happens when you increase the temperature? Okay, before that you have to understand that these particles, okay, which is having higher energy, they can form products. Okay, because you know we have understood that first one activated complex has to be formed which is having higher energy. So that is why these I can say the molecules which has energy in this region, they can form products. So now again let us see the graph. So this is the Boltzmann curve. Okay, this is the Boltzmann curve at temperature T. Now when you increase the temperature by 10 degree, T plus 10 degree, you see the graph has changed like this. Now what you observe here, these are the particles. See, this energy is the energy of activation. So those particles having energy more than energy of activation will definitely react, right? So earlier when the temperature was T, we found only these particles, only these many particles were there and they were able to form the product. Now when you have increased the temperature by 10 degree, the number you can see here has increased, right? This area shows the fraction of molecules which react at 10 plus 10. So the number of molecules which can react at higher temperature is increased, right? Earlier suppose 5 molecules were reacting, now you can see 5 plus another 3, suppose 8 molecules are reacting. So if more molecules will react, more products will form and the reaction rate will become faster. So basically what is the reason why on increasing temperature the rate of the reaction increases? Because when we increase the temperature, the number of particles having energy more than the energy of activation increases and they can lead to the formation of products. So when we increase the temperature, more number of more number of molecules can form products. Getting? Okay, now let's talk about the third factor, that is effect of catalyst. Okay, so catalyst is, first of all you have to understand what is a catalyst. So it is a substance which increases the rate of the reaction without changing anything permanent in the reaction. Okay, and how does it do that? It provides an alternative pathway of the reaction by reducing the activation energy between the reactants and products. So if you see the Arrhenius equation, let us go back and discuss this Arrhenius equation. K equal to A into e to the power of minus Ea by RT. So for easy understanding, let me write like this: A into e to the power of Ea by RT. Now just assume that if activation energy decreases, this whole term will decrease, this fraction will decrease, right? After that, if you see Ea by RT, this fraction also decreases. Now if this fraction decreases, overall e to the power of Ea by RT, this value will also decrease. Now if this value will decrease, then what will happen? K will increase, and the value of K will increase. So here we have a catalyst is something which can reduce, which can faster the reaction by doing what? By providing an alternative pathway which has lower activation energy. Next, a catalyst does not alter Gibbs energy and equilibrium constant. Okay, equilibrium constant and Gibbs free energy value does not change here. So now let us understand this through a graph. You can see that first of all the first solid line which you see, it is the reactant energy is here and product energy is here, and this is the activated complex energy. So when you have without catalyst, you need this much activation energy for the reaction to happen, right? This is, but when you have energy of activation without catalyst, but when you add catalyst, what will happen? It will provide a different pathway which is having lower activation energy, and when the activation energy is lower, the K value is increased, and that is why rate of the reaction increases. Now let me tell you that this diagram is very, very important and is asked often in the exam. Now moving to the next last topic, that is collision theory. So what does collision theory tells us? See, according to this theory, it is very simple, that the reactant molecules must collide with each other to form products. Okay, that is the collision theory. The reactant molecules are assumed to be hard spheres, and the reaction is postulated to occur when the molecules collide with each other. Okay, now is that every collisions, whatever, if they collide they can form products? No, that is not the thing. We have some other conditions, some constraints are there to the collision also. So first of all, let us understand what is this term collision frequency. So it is the number of collisions per second per unit volume of the reaction mixture. In 1 second, in 1 unit volume, how many molecules are reacting with each other? That is called as collision frequency. Okay, and another factor which affects the rate of the chemical reaction is definitely activation energy, right? Lesser activation energy, higher the rate of the reaction. So considering all these factors, collision frequency and the activation energy, the rate was given earlier by collision theory as ZAB into e to the power of minus EA by RT. This is pretty similar to your Arrhenius equation. Okay, so let us first understand this in detail. So see, collision theory provides why behind our observations of the reaction takes place. It is simple yet a powerful model based on the central idea that for a chemical reaction to occur, the reacting particles, the atoms, ions or molecules must collide with one another. However, not every collision can result in the reaction. Every collision will not result in the reaction. The vast majority of collisions are ineffective. Okay, majority of the collisions do not give you reaction. But yes, there are certain effective collisions to form the products, and a collision must overcome two critical barriers. Okay, so to consider a collision to be effective, that it can form the products, you need two important criteria to be fulfilled. Now what is that criteria? The first criteria is the energy barrier. Means they should have, when they collide with each other, they should have sufficient energy to cross the activation energy. Means if they are colliding but they are not crossing that barrier, see for example, if you see the Arrhenius equation, the graph shows you like this, right? You need to reach here, and after that the product will form. So if I have two reactants, they must collide in such a way that their energy reaches to this value or more than that. Okay, if it collides and their energy is less than the threshold energy, then the reaction will not happen. It's the first thing. And the second thing is the orientation factor. Means the collision should happen in the proper direction only. So as we discussed, for example, for HI reaction to form, the collision should be like this, H and I and I, right? So the reactant must collide with each other in this way. Means they should collide with in this way so that this intermediate can form, right? If they are colliding like this, you have H molecule like this and I molecule is coming somewhere like this, and they're colliding like this, then the reaction will not happen. You need to have a proper orientation for that. Okay, these are the two barriers, and if any collision meets two conditions, meets these two conditions, then we can call that collision as an effective collision and it can give you the product. Okay, so what is the successful collision looks like? So first of all, the orientation barrier. Molecules must orientate correctly relative to each other during the collision. The reactive parts of the molecules must come into contact for bonds to break down and bonds to form. And incorrect orientation will result in an ineffective collision even if the energy is sufficient. Okay, collision should happen in the proper orientation. Next, colliding molecules must possess the certain minimum amount of kinetic energy called the threshold energy. So when I draw this one, okay, this is the threshold energy. Okay, so when the molecules collide, they must possess this threshold energy. This energy is needed to disrupt the existing bonds and initiate the reaction. The extra energy required by the average reactant molecules to reach the threshold is called as activation energy. So definitely this energy which is required for the molecules to reach the threshold energy is called as your activation energy, which we have already discussed. So students, with this we have completed this chapter. We have already understood all the important concepts. So in the next video I'll be solving the most important questions from this chapter. Okay, so if you have any doubt, you didn't understand any concept, do let me know in the comment section. I'll take it in the next video. And thank you so much for watching and showing all your love, and do not forget to subscribe the channel, because this channel is going to be your ultimate savior for KCET and PU2 2026, and many more things we have planned which will be coming in the session. And yes, this can help you to get a very good marks, so do consider subscribing it. Thank you so much. Bye bye and take care.